Good afternoon. I'm very glad to invite Harald Pfeiffer of CETA today as the welcome speaker. Harald has done quite important work on many different aspects of numerical-relativity. I would say probably almost all aspects. And furthermore, he's very actively involved in the interface of numerical-relativity with analytical GR as well as gravitational astronomy. And today we'll hear from Harald about the overview of numerical-related binary black hole.
Thank you very much, Cauchy, for inviting me here. I very much enjoy my visit here still, even after 2 weeks. It's too bad I will have to leave tonight. That there's quite a lot of overlap between these talks. So
it helps to hear things close.
Yeah, thank you. Okay, so the topic of today's talks are binary black holes. Two black holes orbiting about each other, losing energy and angular momentum through gravitational waves, and eventually colliding and forming one bigger black hole. We believe this happens in the universe at a fairly reasonable rate. And when this happens, the energy emission of emerging binary black holes in, say, watts per second is comparable to the entire energy emission from the rest of the universe combined. So black hole, to put this in a different context, if two black holes merge 10 gigaparsecs away, close to the edge of the observable universe, the energy flux passing here through Earth is still roughly 10,000 times stronger than all the light we receive from a full moon. So there's a tremendous amount of energy being emitted by merging black holes. Unfortunately, all of this energy goes into gravitational waves, and we won't be able to see black holes merging in with electromagnetic radiation. Otherwise, they would be way brighter than gamma ray bursts. So this is to remind you of a few basic properties of black holes. They are made entirely of warped space and time. They are vacuum solution of Einstein's equations. And this warpage of space and time basically has three different components. There's a curvature of space, often indicated in this type of embedding diagram by this downward cylinder. There's a slowing of the flow of time close to the event horizon, gravitational redshift, indicated by the color coding here. And there's also dragging of space around the black hole if you have a rotating black hole. Furthermore, the warpage of space and time is so strong that the causal structure changes. The well-known tipping of light cones as you approach the event horizon. And inside the event horizon, the light cones are completely inward pointing. And that's the reason why nothing can escape from black holes. We know these crazy objects exist because we can observe X-ray binaries where we see the donor star and a hot accretion disk around an object which is somewhere between 5 and 30 solar masses, depending on the system. And the orbit is too tight of the companion star to fit a regular star in there. And the object is too massive to be a neutron star. Also, at the center of galaxies, there are very massive, very dense objects. Here's an image of the center of our Milky Way, and the motion of stars around the center of our Milky Way is traced out over the last 20 years. And you see some of these stars within 15 years or so make a complete orbit. And by analyzing these orbits, one can infer that here in the middle are about 4.1 million solar masses within a size of roughly the solar system. Again, we don't really know what else it could be besides a black hole. All other explanations have been ruled out in the meantime. And while preparing this talk, I actually learned about that we now know about a second star close to the galactic center, which has made a complete full orbit. It's called S0102. It's a factor of 16 less luminous than the well-known S02, but it has an even shorter period, 11.5 years. So this was published late last year by Andrea Gese's group at UCLA. So we know of black holes. The other important ingredient about which we have heard a lot already in this workshop are gravitational waves, perturbations of space and time itself, that travel at the speed of light. These gravitational waves are generated by time-varying quadrupole moments. And if you take the quadrupole formula, plug it, take a second time derivative, and do a little bit of rearrangement, basically put one time derivative on each of the positions and turn them into velocities, you will notice that the gravitational wave strength is proportional to the bulk kinetic energy of the source. So to get strong gravitational waves, one needs large masses on fast asymmetric motions. And the large masses are necessary because of this prefactor here. G is a very small number. The speed of light is a very big number in the denominator. And the distance as well is a very big number, as black hole binaries tend to be very far away. And so at the end of the day, typical numbers one arrives at is a gravitational wave perturbation of a few parts in 10 to the minus 22. And Satya 1.5 weeks ago and Bayer this week have talked about how one measures these gravitational waves with gravitational wave detectors. In particular, there's an entire worldwide network that's being under construction or being upgraded. 2 detectors in the States, 1 in Italy, hopefully 1 here in India, and 1 in Japan. These ground-based gravitational wave detectors search for stellar mass compact binaries, so the black holes I'm talking about are one of the prime sources for gravitational wave detectors. And just to put some context on the size of stellar mass black hole binaries, a typical 10^10 solar mass binary in the LIGO frequency band has an orbital separation of roughly the size of southern India. Each of these black holes is about 60 kilometers across, and they move at about 40,000 kilometers per second. Actually, while making this, I wondered how anything in India could move at such a speed, but black holes would manage to. Which is actually truly amazing to have objects about 1 million times the size of the Earth changing the velocity many, many times a second. So there are enormous forces and enormous accelerations at work in these systems. Besides stellar mass black holes, there's also supermassive black holes, as I already pointed out with the graphic about the center of the Milky Way. And supermassive black holes can also form binaries. We believe this happens when galaxies collide, as is happening here in this image from ESO. And 2 upcoming instruments, well actually 1 instrument already ongoing search with pulsar timing array is searching for gravitational waves from supermassive black holes. And also the ELISA mission, the space-based detector, will also be searching for gravitational waves from supermassive black hole binaries. Okay, let me switch over and begin talking about more the core of this talk, numerical relativity. So why would you be interested in simulating black holes? There's several different reasons. One of them is astrophysics. One would like to know what happens when compact objects collide, like black holes or neutron stars, or when stars collapse in supernova explosions. Another reason is to elucidate properties of general relativity. A lot of things can be determined analytically, but once one gets into nonlinear dynamical situations without symmetries, there's usually no other way to approach these than full numerical simulations. And one widely used example of this, and widely known example, is critical collapse of various matter types or gravitational waves that may or may not form a black hole. So here's a plot also from a paper from Matt Chopduik, who discovered critical collapse for Young-Mills type fields, I believe. And the important thing is you can actually, what's plotted here is a phase diagram of initial data, basically. How much the field strength, the field amplitude on the y-axis, and some perturbative deformation parameter on the x-axis. And so what happens is, if you have very weak gravitational fields, very weak fields, the fields will just disperse and you will be left without a black hole, just flat space and outgoing traveling waves. And if the amplitude is strong enough, at some point you have enough matter in your system that it collapses under its own gravity to form a black hole. And so what Matt began asking was the question, what happens in between? And so it turns out if you go up here in amplitude, a lot of different funny things can happen. Here between A and A prime, you can have what's called type 1 critical collapse, where you go from zero black hole mass on the downside to a discrete away from zero mass above. Here on this side, you can actually generate a zero mass naked singularity at that point. And so these type of calculations actually showed us that Penrose's cosmic censorship conjecture is not valid generically, that there are counterexamples. But you need to fine-tune your system you're looking at to actually achieve a counterexample. The main motivation, however, for running binary black hole simulations, at least from my own perspective, are gravitational wave detectors like LIGO. And it turns out these gravitational wave detectors have a very varied need for input from numerical relativity. And so this slide just lists all these different needs, at least those I am aware of. The most widely known one is for signal detection with template banks. You need to know the waveforms you're looking for. And so to compute waveforms usually involves numerical relativity to get the best possible waveforms. And so for signal detection, there is input of numerical relativity into these template banks. Signal detection is actually a fairly straightforward process, it seems to me. One searches only for subspaces of all possible binary black holes. Right now, the state of the art is aligned spin binaries. So if you only wanted to make template banks, all you need to do right now is to simulate aligned spin binaries. That's not too hard. And B, it turns out that the accuracy requirements are fairly modest. So that's an important use of numerical relativity, but not the most challenging from the numerical side. Along with signal detection also goes information about general characteristics of the waveforms that LIGO can use when trying to distinguish between actual signals coming from outer space and detector irregularities, detector glitches, which might or might not look like signals. The more of these detector glitches can be discarded because they look very different from what we expect black holes look like, the easier subsequent data analysis will be. Okay, so now we have detections or we don't have detections. The next step is to actually use this information to decide how many binaries are there in the universe. To make this connection, you need to know the detection efficiency. Are you seeing every single binary in the universe, or only 1% of all binaries? And to do that, you actually also need to know the waveforms for other systems, not just the ones you've been searching for. You might end up searching only for aligned spin binaries, but if you want to make statements about whether or not you could have seen precessing binaries, you better know how precessing waveforms look like, because you need to check whether you could see with your aligned spin searches the precessing waveforms. So here, for this point, we need waveforms essentially everywhere in parameter space, precessing systems, eccentric systems, any type of object that might conceivably exist in the universe. Then, afterwards, another important use is parameter estimation, which is done with Markov chain Monte Carlo simulations. Those require waveform models in all parameters that are to be estimated. Those are typically all the intrinsic ones, the masses and the spins. So here we actually need precessing waveforms, eccentricity potentially. And the important part about parameter estimation is not only to measure the intrinsic properties, which are obviously very interesting, but also very important is to figure out where in the sky the source actually sits. And having good waveforms may very well increase sky localization, which will make it easier to find electromagnetic counterparts. Counterparts are the last point I'm aware of where LIGO can benefit from numerical simulations, essentially answering the question, what type of signals should electromagnetic telescopes or neutrino detectors look for, or what should we expect when searching for electromagnetic counterparts? This doesn't happen for binary black holes, but it happens whenever you have a neutron star in the system. So, leaving the neutron stars and electromagnetic counterparts aside, all these points up here require, as primary input from numerical relativity, accurate waveforms. So let's go about and see how one actually can compute those accurate waveforms. LIGO waveforms tend to be quite long with this many cycle lasting early in spiral phase, so long that we can't just do them with numerical simulations alone. For the foreseeable future, we will always attach some analytical approximate solution in the front. Mark talked about this 2 days ago, about the various approximation techniques. And then switch over to numerical relativity for merger and ring down. This is the prototypical signal sketch of a waveform. First, low amplitude, low frequency, and then chirp signal with increasing amplitude and increasing frequency. More realistically, waveforms might look like this. So this is a unequal mass binary with spin, with precession, with the whole shebang. And what one now has in the waveform is a higher temporal harmonics, first of all. So if you look, every second peak looks different. That is because there's now a distinction between the small black hole moving away from you and moving toward you. And also there is now a modulated amplitude, which arises because of the spins. We have precession of the orbital plane indicated down there. And as the orbital plane might be more or less edge on, this impacts the amplitude of the gravitational waves. The waveform will look different depending on the overall inclination of the source. This is a moderately precessing binary, so there's a reasonably well-defined average inclination. And what's not obvious here, the phasing of this in-spiral waveform is also modified as compared to this non-spinning waveform plotted here. But to the eye, both of these look like sinusoidal curves, and one actually has to look more carefully to find this different phasing. But the phasing is perhaps the most important aspect here, because LIGO is doing phase-coherent matched filtering, so we want the waveform to be accurate to a small fraction of one cycle. Okay, so how does one go about numerical simulations? The basic idea has been known since more than half a century. So the goal here is to find a space-time metric GAB that satisfies Einstein's equations, which in vacuum simply means the Ricci tensor must be 0. The first step numerical relativity does is it takes this nice 4-dimensional space-time of Einstein and cuts it back into space and time by introducing hypersurfaces. The first one we shall call T1, the next one T2, the third one T3. And so now T is our time coordinate, and for each time there is one hypersurface. If you look at Einstein's equations and make this 3+1 decomposition, the equations split in equations of 2 different characters. One of the equations are evolution equations that have d by dt in them that tell us how certain quantities evolve from time slice to time slice. And the other set of equations do not have any derivatives in them. They only have, they don't have any time derivatives. They only have spatial derivatives. So these are consistency conditions that restrict the allowable data within each hypersurface. The situation is perfectly analogous to Maxwell's equations, where you have the curl equations that tell you how E and B evolve forward in time. And you have the divergence equations that restrict the set of allowed physically reasonable E and B fields. Maxwell's equations are nice and simple, linear, simple flat space equations, these here are quite a bit more involved. So the basic strategy has been clear for many decades. So why is it so hard to do this? We have singularities inside black holes. It turned out that for many decades, the constraints, these extra consistency conditions, were very hard to preserve. Essentially, any evolution one did led to the constraints increasing exponentially in time. And so very quickly, the calculation was meaningless. There's a coordinate freedom. Einstein's equations has the nice property of being coordinate invariant. You can pick whatever coordinates you like. But we are faced with the choice of having to choose a coordinate system for a space-time we don't know yet, which we are just about to solve. And besides these more conceptual issues, the numerics also was quite challenging, depending on how one writes Einstein's equations, between 20 and 50 variables, of the order of 10,000 floating point operations per time step per grid point. They are different length scales, small black holes, long orbital periods, and even further away distances to wave extraction. And we have high accuracy requirements.
Why are the constraints difficult to preserve?
I don't know, because if you can answer that question, then it's no longer difficult. So it turned out that essentially in most ways, when people wrote down Einstein's equations, there were unstable modes, constraint violating modes, which grew exponentially. And so one of the key features that actually made everything work around 2005 were the realization of how one can control these unstable constraint violating modes. It doesn't happen with Maxwell's equations. Well, yeah. Yeah. Mm-hmm. Yeah. Okay, so the first foray into numerical simulations was made 50 years ago, 49 years ago. And they took a big supercomputer, an IBM 7090. Actually, Susan Hahn is at IBM, curiously enough, or was at IBM back then. And grid size of 50 times 150 grid points, 4 minutes per time step, 50 time steps. Total evolution time 1.8. So this number is in the same units as I will be showing you many other time plots later on. So remember, back then, state of the art was 1.8. The whole history of numerical relativity is quite a bit more complicated and basically falls into 3 stages. There is what one can call an early stage, which ends, give or take, 1998, give or take 1 to 2 years. And I'm highlighting a few of the important results from these early days. And back then, the overall understanding of properties of Einstein's equations and of computers just wasn't good enough to do anything truly useful. And just to give you an example of state of the art at the end of this first phase, there was a binary black hole branch challenge which set out to solve binary black holes, period. And after 4 or 5 years of hard work, they managed to evolve a single black hole for 60 m in time, while it is moving about 2 or 3 black hole diameters. And then after 60 m in time, 10 light crossing times, the code crashed, and that was state of the art. But still, 60 m is about 20 times longer than what was done 30 years earlier. Then came a middle phase, roughly speaking, from 98 to 2005, 2006, where everybody went back to the drawing board and improved various ingredients that went into black hole simulations. So what came out of there is, what do we have? Better initial data, better numerical methods adaptive mesh refinement, better ways of dealing with gauge conditions, alternative ways of how you write Einstein's equations, which are mathematically better behaved from what has been done in the first phase. Ways of dealing with the black hole horizons, thinking about how you actually define spin of a black hole. And perhaps the last one in here is this one here, constraint damping. The people also thought about how can one control the constraint violations. And in 2005, Gundlach wrote the important paper about this, actually showing how constraint damping can be achieved in one of the ways of writing Einstein's equations. Then, of course, the big boom happened in 2005 and 6, where first Pretorius showed us how to do black hole simulations by essentially putting together all these pieces that have been developed here in a very ingenious way. University of Texas Brownsville and NASA Goddard achieved black hole simulations with completely different techniques about half a year later. And we at Cornell Caltech turned out that we could essentially reuse the whole setup of Franz Pretorius and plug it into our spectral code and also get going within a couple of years thereafter. Hey, I want to show this one here. These are the important papers from 2005. Franz Pretorius is one, and then half a year later, Campanelli, Lusto, Maronetti, Zlochova, and Brownsville, and the Goddard group around John Baker and Sean Centrella in Maryland. Again, to give you context for what follows afterwards, these are images from Franz's paper. He could do about 3/4 of an orbit before the black holes merged and then rang down. But the important feature in here is that the code ran actually to the formation of a common apparent horizon and into ring down, and out came a waveform which looked like this. Initially, I won't pretend that I can see an in-spiral signal here, then a merger signal, and at the end, the ring down signal. So at this point, we're actually at 300 M, and the more important thing is that this code is actually stable and convergent. Running at higher and higher resolutions, Franz could extract the solution more and more accurately.
The code did run up to the ring down or up to the merger, or did
It continued through merger and then into ring down. The figure on the left is the trajectory of one of the two black holes. And once the black holes have merged and you have a common horizon about them, it doesn't make sense anymore about speaking about the individual black hole location. And then, of course, this started a whole host of important results afterwards. And if you see the color coding here, the color coding is such that blue things are numerical improvements, gray things are analytical improvements, and purple things are significant results that actually draw attention outside of numerical relativity. Early on, there was only Matt Chopdwick's critical collapse simulations, but as you can see, starting 2005 and thereafter, the amount of significant physics that has been done with these codes has been tremendously increased. Starting with kick simulations of black holes, post-Newtonian comparisons, community-wide efforts to pool numerical relativity simulations, and leading to waveform models, large surveys of parameter space. But despite all these results, work has also continued more on the analytical and numerical side with important new insights into how you best describe radiation. And for instance, Cauchy-characteristic extraction has also come of age in the last few years. All these points I will be mentioning again later on in the talk. So here's a few results from early on. Black hole kicks. This figure corresponds to an unequal mass binary black hole without spin. On the x-axis is the mass ratio. 0.25 is equal mass. The system is symmetric and there's no black hole kick. once you go away from equal mass, you have an asymmetric system with asymmetric momentum emission, and so the remnant will generically have linear momentum in the opposite way, a black hole kick. And so very quickly it was determined that the maximum black hole kick for non-spinning binaries was about 175 kilometers. These simulations were repeated with spinning black holes, with the amazing result that in a spinning black hole collision, the remnant black hole can pick up a kick of order 1% of the speed of light. And also we began looking into how well post-Newtonian calculations actually accrete with numerical relativity simulations. Here's one of the first comparisons that our group did. What's plotted here is a numerical waveform and a post-Newtonian waveform. They agree very well with each other, which validates both and especially validates numerical relativity. But as you get close to merger, you find quite significant phase differences there. So to summarize, today there are two different approaches in use for simulating black holes. One is on the left-hand side, one is on the right-hand side. And they ended up using completely orthogonal techniques in essentially every single step of the program. When setting initial data, the left approach uses initial data that goes from one asymptotically flat end through the wormhole to another asymptotically flat end. Whereas the approach on the right-hand side stops the initial data slice just inside the black hole horizon and excises the interior. The left approach uses what's called the BSSN system with moving punctures. The right approach uses what's called the generalized harmonic system with constraint damping. This is the very system that Pretorius used in 2005. What's happening there is one chooses a coordinate gauge such that Einstein's equations boil down to wave equations acting on each component of the metric. That's fine. That has been known since the 1920s and forms the basis of post-Newtonian calculations. But if you just do that, you end up again with the fact that the coordinate conditions you have assumed when deriving the equations are exponentially violated in time. So the code blows up as so often before. The trick around was introduced by Gundlach in 2005, putting in a new term that vanishes when all is fine. But when the constraints are violated, this term has the properties of exponentially suppressing the constraint violations. So it brings the solution back to the constraint satisfying manifold.
Just portrayed by just by this. The only motivation is that you don't want those exponentially growing things.
Exactly.
And you just portray
yep.
zero whenever it's not required.
Yep. So you go in by hand, modify your Einstein's equations, putting in this term. It's zero when you satisfy Einstein's equation, so it doesn't change the physics, but it improves the behavior when things go bad. In the left-hand approach, this is typically implemented with finite difference codes with adaptive mesh refinement. On the right-hand side, one uses spectral methods within the spec collaboration, which is I'll talk more about this later.
And how are constraints handled on the left
Sorry?
side?
How are constraints handled on the left-hand side? So the BSSN system, Baumgarten and Shapiro, put in an improvement in the late 90s that caused the constraint violations to actually go away. So BSSN was fine since late 90s as far as constraints go, but they had the problem of coordinate conditions. And so here the big breakthrough in 2005, 2006 was the realization that certain gauge conditions actually would lead to stable evolutions. And
just trying to understand this constraint thing. Is it as simple as regularizing the equations by you add a term, it's a very large number, lambda times constraint. So then as soon as that is non-zero,
that's the idea. That's the basic idea.
But how do you set that parameter? That's arbitrary.
That parameter is arbitrary. If you make it too small, the code will blow up.
Right, but then you tune.
Yeah, if you make it excessively large, you will run into Courant conditions. And in between, there's quite a bit of leeway. Okay, so some of the recent technical advances that have been done is the Rochester group actually managed to simulate black holes with mass ratio 1 to 100. So here you have the little black hole going around the big black hole. And what you haven't noticed early on is that the little black hole is actually increased in size artificially by a factor of 10. Otherwise, you wouldn't be seeing it at all. And so this has been a very challenging situation from the calculation from the numerical side. And they succeeded in doing 2 simulations. This is the actual size of the little black hole, 2 orbits, and merge and ring down of that system.
What's the difference between left and right?
2 different camera points of view. This is more like 3D-ish, and this is a top-down view. Our own group has succeeded in computing black holes with very high spin. It turns out a widely used way of constructing black holes in numerical relativity is called puncture data, and that only works for spins less than approximately 0.9. So what's shown here is the first simulation with spins bigger than 0.9, 0.95 in this particular case. And we have done since then, Geoffrey Loveless has done since then 0.97, and he has almost finished a 0.98 simulation. You might ask, why is this important? 0.93 sounds big enough if the maximal spin is 1. The reason is that for Kerr black holes close to extremality, the usual spin is not a good parameter to think about this. It's more useful to think about 1 minus spin squared square root. If you look at the Kerr solution, this is the quantity that shows up all over the place. And that's the expansion parameter around extremality. So for 0.93, spin of 0.93, this parameter here is still only 0.37, only 1/3 its value at 0 spin. And so you're still far away from extremality. And even 0.97 is only a little bit better with 0.24 instead of 0.37. And if you wanted to push this parameter down to, say, 5%, you need black hole spins of 0.999. So there's still quite a way to go. Also, Cauchy-characteristic extraction has been improved significantly over the last few years. For the participants of the workshop, Dennis Polny talked about this yesterday morning. Let me illustrate this in the space-time diagram here. A usual 3+1 code has these space-like hypersurfaces indicated in green here, which end at some finite outer boundary. That means you also need to compute and extract gravitational radiation at some finite. Also, Cauchy-characteristic extraction has been improved significantly over the last few years. For the participants of the workshop, Dennis Polny talked about this yesterday morning. Let me illustrate this in the space-time diagram here. A usual 3+1 code has these space-like hypersurfaces indicated in green here, which end at some finite outer boundary. That means you also need to compute and extract gravitational radiation at some finite radius, where it's still tainted by coordinate ambiguities. What Cauchy-characteristic extraction does is it reads off data from the green 3+1 code at a certain distance, and then, while still solving Einstein's equations, propagates that data all the way out to future time like infinity, where gravitational waves are unambiguously defined. So that way you can actually get waveforms out that have far less coordinate ambiguities than the finite radius ones. And the last point I wanted to make here is progress in describing precessing waveforms. First, focus on this right picture here. What is shown here is the, let me actually put myself in front of the left picture so you're not getting distracted. What is shown here is the circle harmonic decomposition of the outgoing gravitational waves. The 2-2 mode is big, then comes 4-4, then comes 6-6, and then comes some other mode. The point to take away here is there's only a few relevant modes that one has to worry about when simulating non-precessing binaries. So all this looks nice and good. The problem arises on the left-hand side. If you have a precessing binary, the orbital plane changes around, and it turns out all different YLM modes get excited. Early on, the orbital plane is still in the XY plane, and you have this nice separation of scales. But then as the orbital plane precesses, you notice a whole mess showing up here. And with ideas first developed by Schmidt and O'Shaughnessy and then refined by Boyle et al., the numerical-relativity community figured out how to deal with this mess, essentially by going into a frame that is aligned with the instantaneous character of the emitted radiation. As the orbital plane precesses, this frame will also track the orbital plane precession, and that way you can restore the simple structure of the radiation despite having precession. And this picture here is actually still the precessing binary, just represented in this well-adopted frame. Okay, so much for some generic overview, and I'm running way late, so I will have to speed up a little bit. What follows hereafter are results of my own work with my own collaboration. Our name is SXX, standing for Simulation of Extreme Spacetimes. That's a collaboration between Cornell, Caltech. It then has expanded to CETA, to Cal State Fullerton, to Oberlin College, and to WSU. And the work I'm presenting here involves quite a lot of different people, but this is not all we have in the collaboration. Our goals are to solve Einstein's equations accurately enough for LIGO's needs. So, and this will be the right-hand side of the two techniques of solving Einstein's equations. One slide about our techniques. We're using what's called spectral methods, where we expand solutions as a series in spatial basis functions, like Chebyshev polynomials or Fourier series, and then evolve these Fourier coefficients forward in time. So if you want a pictorial representation, you can think of spectral methods more like a Fourier decomposition, whereas finite differences are more a discrete representation of your solutions at the grid points. We combine this with black hole excision. Because the light cones tip over, we are able to place an artificial boundary inside the event horizon, which is a pure outflow condition, so we don't need boundary conditions there. This allows us to avoid the singularities in the middle. And we then combine spectral methods with black hole singularity excision by a rather complex domain decomposition. First having spherical shells around each black hole, then putting cylinders at intermediate distances, and then putting more spherical shells to large outer radius. This decomposition is necessary because you can only do spectral methods in very simple shapes like cubes or cylinders or spheres, but not in something with two excised spheres. It's also necessary to allow us parallelism. We parallelize by putting different subdomains on different processors. And it allows us to tune resolution where we need it, putting high resolution close to the black holes and only fairly low resolution far away. Close to merger, the domain decomposition looks even more bizarre because the black holes deform under their mutual gravity and spin interactions. And so that the grid might look something like this, where Mark Shade and Bela Selaci at Caltech have put in tremendous work over the years to figure out how to do black hole mergers with spectral methods. To put some context on this whole endeavor, the code is about 500,000 lines long. We have developed it since about 2000. And my rough estimate is that we've spent about 50 person years developing this code over the years. And so far, we've had about 80 publications, increasing quite rapidly. All the simulations I've been showing you, and I will be showing you, again to give you context, require about tens of CPU years, 100,000 CPU hours each, spread out over a couple of months of wall clock time. So putting all these things together, this was our first grandiose simulation in 2007. 2 equal mass non-spinning black holes orbiting about, eventually coming closer and closer. The movie will fast forward. The plane down here shows the equatorial plane, a spatial Ricci scalar, color-coded by the rate of flow of time, and arrows denoting frame dragging. Black holes merge, settle down, and we have our final merged black hole. Out of this, of course, also come the waveforms, which is our most important deliverable. And with the waveform, so you see the in-spiral chirp as usual. And at the end, here in this log-lin plot, you see very nicely the exponential decay as the remnant black hole rings down to a stationary quiescent black hole. One important aspect of why we use spectral methods is they allow us very, very high accuracies. Here's the same simulation running six different time at different resolutions, and I'm plotting here the phase errors on a log scale. And we observe roughly exponential convergence, which is the big benefit of spectral methods. When they work, or if they work, they typically are more accurate and more efficient than other techniques. And this is what allows us to do longer simulations and by now also more numerous simulations than other groups. In the past, the more numerous wasn't true because until Mark and Behler fixed all our merger problems and upgraded the merger technologies, we had significant problems simulating the merger of black holes. Okay, so out of this comes now a lot of eye candy. Here's a 6:1 space-time diagram, big black hole in the middle, little black hole orbiting around, orbital trajectories for unequal mass simulations. And having these types of simulations and careful error analysis, one can now go off and for instance, validate against post-Newtonian. What you validate will depend on your point of view, whether you're trusting numerical relativity or you're trusting post-Newtonian. But if you look here at early on, this is the difference between post-Newtonian and numerical relativity early on. And focus here as I increase the post-Newtonian order, you will notice that everything begins to agree more and more well. So we seem to have agreement between post-Newtonian and numerical relativity, validating each other in the process. Of course, close to merger, you see things still go quite bad. This is more easily seen when you just plot post-Newtonian numerical relativity on the same plot. On this particular plot, it looks perfectly fine, which was one of the big astonishments around 2006 or so. That post-Newtonian seems to be absolutely correct until we in the numerical relativity community realized that there's not a single way of doing post-Newtonian, but essentially an infinitely many variations of the same theme. And it turned out that the one post-Newtonian version, one we looked at first, happened to work perfectly well, but others worked much less. So coincidence. One problem is now at this point, there's absolutely no a priori knowledge which version of post-Newtonian might be working well and which one wouldn't. That point is driven home at this plot, which does the same comparison at different mass ratios. So at mass ratio 1, there's this one blue post-Newtonian approximant, which had essentially 0 phase difference with numerical relativity. And the other one I was showing you was Taylor T1, this one up here, which is quite different. So if you just look at mass ratio 1, you might conclude, oh, Taylor T4 is the best there is. But if you now repeat this at different mass ratios, you actually notice Taylor T1 gets worse and worse, and the other ones seem to be getting better. So not very clear. In fact, the whole notion of trying to identify a post-Newtonian version that works best, I think is a fool's errand, because what this type of plot shows is this uncertainty arises because of higher order terms that were neglected in post-Newtonian. So my suggestion of reading this type of plot is essentially to take the area traced out by the different post-Newtonian approximants as a measure of the truncation error of post-Newtonian. And as you can see, within this shaded area, all these approximants are consistent with 0, so they are all consistent with numerical relativity within their respective truncation errors. Okay, post-Newtonian gets worse and worse the closer to merger you get. So one important question that arose over the years is, how long can you trust post-Newtonian? Can you run post-Newtonian all the way to just before merger and then switch over to numerical relativity? Or do you need to stop post-Newtonian quite a bit earlier and do more work in numerical relativity? Both these curves look perfectly nice sinusoidal squiggly curves, but if you look carefully early on, here's a dephasing of half a cycle. So while both look nice, this dephasing already indicates that the first one up here might not be good enough.
Are you sure this is not just like a constant phase shift or a linear phase? It's not really relevant?
So these are aligned at merger, so the numerical relativity waveforms are completely identical. We could align them in post-Newtonian, then the numerical relativity part would be out of phase. This is just meant to be an illustration that it's important where you truncate post-Newtonian. This is not meant to say, this is a bad waveform. You need to be more careful to actually analyze in more detail how the post-Newtonian errors impact your data analysis. And the next 5 slides were supposed to do that, but I'm running out of time. So I will skip them and just tell you there's 2 different ways you can interpret how long numerical relativity simulations need to be. One way is the practical approach. Well, we need something for LIGO in 3 years from now, and it needs to be good enough to find waveforms. And for that approach, something like 10 orbits of numerical relativity seem to be sufficient, which is perfectly achievable. Then there's the perfectionistic approach. LIGO costs $500 million. We better make sure we can extract as much science out of LIGO as we anyhow can. And to extract all the science turns out to be more difficult than just to finding waveforms. And so it turns out, if you want to go the perfectionistic route, you're being led towards order of 100 or so numerical relativity orbits. So there is no one answer, but somewhere between 10 orbits is the minimum, and there are reasons to go to hundreds of orbits if you are crazy enough and want to punish yourself and do that. But I would rather like to spend the rest of my time on more recent things. How are we doing in actually exploring the big black hole parameter space, and how are we dealing with precession? So there have been several community-wide efforts to compute waveforms for binary black holes, where all the groups combined forces to attack the problem. The first one was in 2008 and ended up with 20 waveforms of a length between about 200 m and about 2000 m. The second one was in 2012, the Ninja 2 collaboration, ending up with 40 waveforms, so twice as many. Average length about 1000 m, the longest ones 3,000 to 4,000 m. They all appear long here because the red pieces are post-Newtonian waveforms that have been attached to the numerical relativity ones. So we are making progress in terms of sheer number and length. Unfortunately, we are still, at least as far as published peer-reviewed work goes, we still have a big lack in parameter space. This is again the 40 simulations of Ninja 2. They are all aligned spin, no precession at all. And it turns out the waveforms end up either on the equal mass, equal spin line, or on the unequal mass, zero spin line. So we haven't even sampled this three-dimensional parameter space in any depth. Of course, beyond aligned spin systems lies the vast space of precessing waveforms, where you pick up, this is not a movie, too bad. This is supposed to be a movie, where you pick up, which you enter by having spin directions which are not parallel to the orbital angular momentum. Once you have non-aligned spins, the spins will precess around, and the orbital plane will precess around. Here you see a case of rather modest precession and the corresponding waveform. Here you see a case where the orbit actually almost flips over by 140 degrees, and again corresponding waveform in a certain sky direction. And as you can see, the modulations that come from precession can be quite extreme. In particular, in this gravitational wave polarization, because the sense of rotation of the orbit has switched, these sharp features in the waveform that first were going down now suddenly go up. So there's a lot of variety and structure in these systems. And to get there, to simulate these types of systems required, again, quite a bit of technical code improvements, which were done by my graduate student, Sergei Osokini. Putting all these pieces together and having plenty of computing time, over the last roughly 4 years, we have managed to assemble 171 simulations, ranging from mass ratio 1 to mass ratio 8, most of them between 1 and 2, the easiest cases, with a length of approximate of about 20 orbits or so median, longest ones about 33 orbits. And so this would be the current state of the art compared to the 1.8 simulation in 1964. You probably can't see the scale from back there. Each little tick here is 2000 M evolution time. So we were able to make the waveforms longer, plus simultaneously do more choices of parameters, plus also keep quite high accuracy. These are the waveforms plotted in a certain sky direction. The sky direction is chosen such that if you have a non-precessing system, like the one up here in the corner, the second gravitational wave polarization is identically 0. So wherever you see a golden straight line, those are non-precessing systems. And whenever you have a significant contribution of this golden mode, those are the strongly precessing systems. The whole effort took somewhere between 3 and 4 years and in excess of 50 million CPU hours. I just alluded to, we still have quite good accuracy in these simulations. Here's my favorite one, simulation about 10,000 M long. Down here's a convergence test, and we achieved the same absolute phase error that we achieved earlier on for the 4000 M equal mass non-spinning simulation, despite this one being 3 times longer, having unequal masses and having spins. So you can now go off and do nice pictures. Let's focus on the left one here. This is the orbital angular momentum going around a precession cone. This is the spin going around a precession cone. We're in the process of comparing this to the post-Newtonian precession equations. The blue jagged curve is the numerical-relativity orbital angular momentum, which follows a precession cone with slightly increasing opening angle. And the light blue smooth curve is a fit performed in the first quarter cycle here to the post-Newtonian precession equations. And while only fitted in the early part, the post-Newtonian precession equations nevertheless reproduce numerical relativity remarkably well throughout. Okay, one big question here is where do we go next in terms of numerical simulations? 171 sounds very impressive, That's why I threw in this slide, just to show you how much work remains to be done. The left panel here shows the mass ratio. 0.25 is equal masses. 0 is infinite mass ratio, test mass limit. Here is the spin magnitude on the big black hole. And color-coded is this by the component of the spin along the orbital angular momentum. And as you can already see, almost all simulations are between mass ratio 1 and 2, and almost all simulations have spins of 0.5 or less. We chose spins of 0.5 or less because 3 years ago, we knew we could do this region of parameter space, and our approach was, let's just use our big computer we have here and do something, and leave the more complicated stuff for later. For the small black hole, it looks even more extreme. Again, mass ratio 1 and 2, spins up to 0.5, but as it turns out, almost all, a very large fraction of these simulations have small black hole of 0 spin. So there's this quite large region of parameter space which remains totally unexplored. Plus, the spin directions are also very coarsely sampled right now. One is about waveform models. So you have this discrete numerical relativity simulations and want now to construct waveform models for our collaborators at LIGO. One approach is the so-called phenomenological models that Archive is spearheading. The second approach I'm more familiar with and more deeply involved is called the effective one-body method. It's, from the mathematical side of things, way more complicated than the other one. You basically start out with a formalism developed in the late 90s by Bonanno and Damour, and then which gives you quite complicated expressions for an effective Hamiltonian and some other terms. And then you put in new terms by hand in strategically chosen places and fit those terms to numerical relativity simulations. In the past, we've done this for non-spinning binaries and for aligned spin binaries. And so here's one example from the aligned spin EOB model. This plot shows the numerical relativity waveform and the post-Newtonian waveform. One is red, one is blue. And they are hard to distinguish because they are throughout the entire simulation within a line thickness of each other. So this worked actually remarkably well for the aligned spin models. What we are right now about to finish, or rather our collaborators at Maryland, Yi Pan, Alessandra Bonanno, and Andrea Tarachini, is a first precessing EOB model. The idea here is to evolve the EOB orbital dynamics with precision. You solve for the orbital phase, orbital angular momentum, and the spin vectors as a function of time. You then take the aligned spin waveforms we had computed earlier and rotate them into the frame that is aligned with the orbital angular momentum. And so in this model, there is no new numerical relativity tuning going on. It's still only the aligned spin tuning. But nevertheless, for the two cases that we have compared so far, the agreement is utterly remarkable between numerical relativity simulations and this new precessing EOB model. So here again, blue is numerical relativity and red dashed is EOB. And this time around, you can actually see a little bit of dephasing and amplitude differences during merge and ring down. Here's a different case, again, very small differences. But nevertheless, the sheer fact that without any additional tuning, this works so remarkably well over 50 cycles, and even in merge and ring down, differences are very, very minor, is quite impressive. A second approach we've been pursuing quite lately in collaboration with Duncan Brown at Syracuse is to do away with EOB and phenom completely and to do numerical relativity-based template banks. A usual template bank for LIGO might look something like this. Here's M2 and M1. The points are scattered all over the place, and so the traditional view is to do this with numerical relativity, you will need to simulate each point here for something like several thousand simulations. However, we have this nice property that binary black holes are scale invariant. So if we simulate a mass ratio 1 binary, we can rescale it to get the waveform along this entire one-dimensional line of the mass 1, mass 2 plane. Similar for mass ratio 2, 3, 4, 6, and 8. So we can actually set up a template bank like this with these types of templates. It's not completely optimal as the other one might be. But it turns out, if you take this template bank, and it is perfectly adequate as is with just purely numerical relativity to cover the high mass region above total mass of, say, 50 or 60 solar masses, and up to mass ratio 10. So this region of parameter space could in principle be searched with purely numerical relativity templates without any modeling errors due to waveform fitting, without any difficulties due to EOB or any other model. And it also turns out it's possible to extend this further down. We've looked at what needs to be done to extend this down to 12 solar masses, which is the customary boundary where post-Newtonian searches are effective. And so if you wanted to push numerical relativity template banks down to 12 solar masses, you end up with 26 different mass ratios, and each one must be about 40 orbits long. So it's nothing we have in hand today, but those numbers are perfectly feasible and achievable within a year or so. So it's certainly possible to construct numerical relativity template banks only as yet another approach to providing template banks for LIGO, besides post-Newtonian only and analytical numerical relativity combined models. And that's all I wanted to show. So I'm leaving you with yet another movie of a precessing spinning black hole binary. What's shown here is the instantaneous orbital plane. It will become somewhat more clearer once the gravitational waves become stronger. So I'll just leave you watching this and say thank you.
If you go back to one of the slides on the orbital flip waveform, if you were to cut off, if you were to pretend that, okay, numerical relativity gave you only a few of those inspiral cycles, okay, from ring down backwards, before the orbital flip actually happened. We could still pretend, okay, UBNR is fine up to that point and stretch and have no clue that actually there was an orbital flip in the system. To stretch this, what I mean is, there could be multiple flips, right? So you've matched this for one flip, but why should I trust UBNR? That could be fine.
So the hope there is that, where's the other plot? Is that the precessing post-Newtonian waveforms, the precession post-Newtonian equations will be good enough. So here, for instance, going forward for 2 precession cycles, the precessing post-Newtonian waveforms work perfectly fine. So certainly my expectation right now is if we now take post-Newtonian and go backwards in time, we could trace out the precession dynamics of the system before the start of numerical relativity.
Yeah, put another way, I would trust the UBNR stitching or any other stitching or calibrating much more if they could reproduce some node result in NR, but perhaps not in a post-hoc fashion.
But this flipping is a very subjective statement now because it depends on the inclination angle. If you have mild precession, if you are looking at the edge on, you can have several flips. So it's not really a good way of characterizing this.
I guess we need to define what we mean by flip here.
So, yeah, going, changing by 140 degrees is good enough. Because we cannot predict such, the waveform mismatch can be
in some sense, in some sense, these systems are once again the best possible outcome. Those are very extreme systems. So a more modest system like more equal mass binaries will not show this extreme behavior and are easier to detect. But those systems exist, And they will be a lot of fun to work with later on and will give us work for many years to come. This, by the way, is, I view this as it is a binary black hole simulation, but I view this as an example of a black hole neutron star binary. So the mass ratio here is 9.5, which you could actually, if you go to SI units, turn into a 1.4 solar mass neutron star and a 10 solar mass black hole and a 12 solar mass black hole. And the black hole spin is only 0.5, so the whole parameters are perfectly sensible, reasonable, and possible. So once you have, if you really have this type of systems in nature, and there's no reason I know of why not, then we need to confront these sooner or later. There's also a small numerical issue here, which I haven't advertised. If you look closely, the waveforms stop here at the right edge of the screen. And this happens not because they go off screen, but because our code crashes just before merger. So doing these extreme systems in numerical relativity is also not a cakewalk right now.
So the reason for code crash is qualitatively similar to like the exponentially rising constraint thing, or is it something else?
It has to do with our spectral methods and the curse of our spectral methods. If they work excellently well. If they don't work, it's a pain. The basic issue is that spectral methods are exceedingly sensitive to having a well-posed problem. If you have anywhere in your problem something that doesn't make sense mathematically, even if it's only one single term somewhere in some boundary condition, the spectral code will blow up immediately. On the negative side, this means that you have to do a lot of more work to get it going. On the positive side, if it works, you can be very sure that things are actually at least mathematically well posed.
So I think that is
and it turns out the more extreme the mass ratio, the more extreme grid deformations we need just before mergers. And we've managed mass ratio 10 non-spinning by now, but mass ratio 9.5 with spins, not quite.
So a finite difference, I mean, is there a program to compare codes, like using these things with finite difference in spectrum, or?
In principle, yes and no. So comparisons have been done in the past for equal mass non-spinning waveforms, and they everything agreed with each other. And together with Sasha Husa and Mark Hannam, we have an ongoing collaboration to actually compare precessing unequal mass simulations against each other. Unfortunately, since we started this collaboration, Sasha and I started faculty jobs, and Sasha and Mark got kids, so it never rises to high enough priority to actually make significant progress.
So does this actually give you a hard constraint on the mass ratio that you can simulate with the current setup?
For automatic simulations, yes. For if one is willing to put enough manual labor in, our present expectation is that with enough work we can expand to larger mass ratios.
The deformations are larger because the tidal forces are larger for small black holes?
Yeah. And another point I didn't advertise is that we think it's possible, but also it may be a lot of work. Where is where's this here, this diagram? A fact I didn't advertise here are these little arrows going to larger mass ratios and going to higher spin. Each one of these arrows was roughly 1 to 2 years of work. So we are further along than ever before, but there might be more arrows in this diagram we just haven't noticed yet.
Diagonal arrows go as square or they add?
So far, there was one diagonal arrow getting in the quaternion control system for handling precession. And right now, this seems to have taken care of all the spin directions. So I'm actually quite hopeful right now that that precession doesn't introduce any additional complexity.
No, you talking about the increasing mass ratio as well as aligned spin.
And this will be difficult as well, yes. And it's more difficult on this one. It turns out to have spin on the small black hole is harder than spin on the large black hole.
It's probably presumably it will have a smaller effect also.
Yes, luckily it has a smaller effect. If you wanted to hear about these extreme spin cases, I suggest you get in touch with Geoffrey Lovelace. He gives amazing talks about them, how difficult they are to simulate. Geoffrey is our high spin expert who fearlessly goes where no man has gone before and actually tries to do this spin 95, 97, and 99 simulations.
Talking about construction of template banks, and especially if you want to create the waveforms in different directions for processing ones. Well, for non-processing ones, that's not a problem, and we do it analytically by using the projection operator, essentially, right? At least for the 2D model. But are you suggesting for processing waveforms that may not be possible? And because you mentioned at some point that you numerically have to get the different slide position.
So for
because the modulation effects will be different.
So what happens is, say you start out with a plain old non-processing binary in the XY plane, as we always do, and as also you guys do with waveforms. In that case, the waveform is totally dominated by the 2-2 mode. If you now just take the simple waveform and rotate it about by some rotation matrix, just an overall rotation of inertial coordinates, the 5 different M modes will all mix. And all 5 L equal 2 while M's will contribute to the final waveform. And it's by no means guaranteed that the 2-2 mode in this rotated frame is still the dominant one. And so once you have processing waveforms, you will always have to think about at least about all the 5 L equal 2 modes.
When you have supermassive black holes colliding, merger, the early stages, there now observations have shown that you have small bulges of pores when they're separated by 1 kiloparsecs or so. They are actually, you will see them in near infrared, they're like small bulges, small pores. So is that taken into account in the simulations? Because that means they're surrounded by small bulge of stars, which will affect the evolution of the black hole and the spin and all that as it's merging with the other.
So at the separation of kiloparsecs, the dynamics of the black holes is totally dominated A by Newtonian gravity and B by all the matter that's around the binary. At that large separation, gravitational waves are totally irrelevant, and it's dynamical friction that drives the black holes together. By the time these simulations become relevant, this might be the last year or so of the binary black hole in spiral, where the separation is only a few astronomical units. And at that point, it is believed that the matter and the stars will be unimportant. So, short answer, no, we don't take this into account. Yeah.
There are parts of this parameter space which are harder to do simulation. Is there some kind of complementarity where you can sort of say that you need to do fewer cycles of simulation, maybe post-Newtonian is better at this large mass ratios or something?
Thank you for asking. No. No is the short answer. So here is a plot I skipped over. This shows the error due to post-Newtonian if you stick to 12 orbits of numerical relativity. For equal mass, things are reasonably good. For unequal masses, things go much worse. It goes the other way. The harder simulation need more cycles. And it seems to be going Yet the harder way, if you want high mass ratio and spin, Satya was talking about this last week, you need even more cycles. It turns out post-Newtonian seems to be least accurate precisely in those regimes where numerical relativity is hard. And so one of the realizations we've gone through in the field over the last 5 or so years is that our 2005-2006 euphorism that, oh, we are done, we can do equal mass non-spinning, was a little bit too early, because it turned out that equal mass non-spinning was the simplest binary black hole there is, the easiest.
What other analytical approaches, do they have some complementarity and effective one body?
So effective one body has complementarity in that it builds in the test mass limit analytically. So the way effective one bodies is constructed, it is guaranteed to give the right answer in the extreme mass ratio limit. So in that regard, it's actually quite nice. But still, you need to fix various free parameters with numerical relativity simulations, and then the EOB supporters announce. Indications are that it actually does, but nevertheless, LIGO is asking for confirmation, and they're very right doing so, because it's a ridiculously complicated formalism.
So, since you said that, you mentioned that you revealed that you didn't have the part of the multi-rhythm waveform for those orbital flip waveforms.
Yeah.
But now you're trying UV-NR, more complete waveforms with that. But UV-NR is not going to predict those missing parts, right?
That's a good question. EOB can predict anything, like string theory. so I'm absolutely certain that the EOB model would generate a waveform for this particular configuration. I just don't know how close to the numerical waveform it would be. It would be a credible looking waveform. It has wiggles of increasing frequency. It has precession effects. The question is, are all these features correct or not?
Yeah, let me ask the last question. Are you expecting any more major technical progresses that would make it possible to do this high mass ratio or simulation?
So progress comes from at several fronts. The most immediate progress that has been happening over the last 2 years already is that our simulations have become much more efficient than they were beforehand. What sets in there is a law that I don't know what the name of is, but the law is that computer simulations always take of the order of months. So yes, our simulations have become faster, but we have immediately then went off and made them longer, or went towards more extreme regions of parameter space. So we are certainly gaining by having the code more efficient. That, I believe, gives us a factor of 10 or so over the last year. We also have 2 longer-term ongoing research projects. One for going to implicit time stepping, which would make high mass ratio simulations particularly more efficient. And the other one is in GPU computing, to use GPUs to speed up the codes even more. It turns out both these approaches are quite difficult to do for technical reasons, so there's no truly outstanding results to show just yet.
Okay, thanks.
Thank you.